Picture the Himalayas for a second. Absolutely breathtaking landscapes, right? But there's actually a pretty deadly reality hiding inside all that beauty. You see, when heavy monsoons hit that steep, unstable terrain, entire mountainsides can literally collapse in seconds. We're talking about roads, homes, and lives wiped out with almost zero warning. But what if we could predict exactly where these hidden death traps are? Well, welcome to this explainer. Today, we're going on a seriously fascinating journey to see if advanced algorithms and AI can actually outsmart the chaotic forces of nature. Let's get into it. So here's the roadmap for our explainer today. We'll start with the Himalayan landslide threat, move into the 13 clues to collapse, dive into the great algorithm face-off, take a peek inside the machine's mind, and finally, look at mapping a safer future. All right, part 1, the Himalayan landslide threat. To really understand the science here, we have to grasp the stakes. In East Sikkim, there's a rapidly urbanizing area called the Ranikhola River Sub-Basin. And when heavy monsoons roll through, they turn this complex terrain into a highly volatile environment. To put the sheer scale of this danger into perspective, you just need to know one critical number: 237. That is the exact number of documented historical landslides in this specific basin alone. This isn't a one-off freak event, it's a persistent structural hazard. And if you map out those 237 historical landslides, they aren't just randomly scattered out in the wilderness. They cluster dangerously close to crucial transit roads and rapidly growing towns like Gangtok and Ranikhola. The danger is, quite literally, knocking on the doors of these communities. Moving on to part 2, 13 clues to collapse. So, how do we predict the unpredictable? Well, researchers gathered data on 13 specific environmental clues, things like elevation, vegetation cover, distance to rivers, and soil moisture. All of these condition a mountain for a landslide. But here's the catch. They don't all carry equal weight. Two factors are the absolute primary culprits. The steepness of the slope accounts for over 23% of the influence, creating this immense gravitational stress. And then annual rainfall accounts for nearly 17%, which basically saturates the soil and acts as the ultimate trigger for a collapse. But how does a computer actually see these clues? It reads them as distinct spatial data layers. Imagine taking an isolated map for slope and another for annual rainfall, turning them translucent, and then stacking all 13 of these layers right on top of each other. Wherever the darkest, most dangerous data points overlap across all those layers, boom, that's exactly where the algorithm pinpoints the highest danger zones. Which brings us to part 3, the great algorithm face-off. Now, identifying those danger zones requires some serious computational heavy lifting, and it actually pits traditional decision-making models against modern machine learning. But before they can battle it out, they all need the exact same baseline clues. Enter AHP and Entropy. AHP, which stands for Analytical Hierarchy Process, relies on human expertise to judge which factors matter most. Entropy, on the other hand, is purely mathematical. It looks for objective uncertainty and variability in the raw data itself. By blending human knowledge with raw math, researchers created this perfect numerical bridge that translates terrain data into a language the algorithms can actually understand. With all our clues weighted, it's time to introduce our rival factions. In one corner, representing the traditional approach, we have the multi-criteria decision-making models, TOPSIS and VIKOR. These guys are highly methodical, strict rule-following systems that rank areas based on mathematical distance from an ideal, safe state. In the opposite corner, the modern heavyweights, machine learning algorithms, specifically random forest and artificial neural networks. These are incredibly complex, pattern-finding systems built to learn, adapt, and spot hidden interactions in the data. Let's look at part 4, inside the machine's mind. I want to peek under the hood for a second to see how these models actually think. Take the random forest model. It doesn't just make one guess. Actually, scratch that. It makes hundreds of guesses by building different decision trees using random subsets of our clues. Think of it like a massive committee of experts. Each tree looks at a slightly different piece of the puzzle and casts a vote on whether a landslide will happen. The final prediction? It's decided by a majority vote. This keeps the model from jumping to conclusions and makes it incredibly robust. Then we have our other machine learning contender, the artificial neural network, which honestly acts like a digital brain. It takes in all our clues through an input layer, but the real magic happens in the middle, the hidden layers. These interconnected artificial neurons are mathematically weighing inputs over and over again, spotting invisible, highly complex, nonlinear relationships in the terrain that a rigid traditional model would completely overlook. And finally, part 5, mapping a safer future. Okay, the moment of truth. Which algorithm successfully predicted the true hazard zones? Well, machine learning absolutely crushed the traditional methods, no contest. When we look at the F1 scores, which balance precision and recall, the traditional models TOPSIS and VIKOR scored a 0.64 and 0.63. Not terrible, but our artificial neural network scored a 0.94, and the random forest achieved a staggering 0.96. In the totally chaotic, complex terrain of the Himalayas, the adaptive nature of machine learning is, for sure, the superior tool. So, why does a 0.96 accuracy score actually matter? Because predictive power equals targeted mitigation and ultimately saved lives. This isn't just some academic exercise. With near-perfect susceptibility maps, regional governments and urban planners can literally see the invisible threats. They can enforce strict building codes, design specialized drainage for unstable slopes, and, most importantly, stop building roads and infrastructure in hidden death traps. By blending the topographical realities of our planet with the sheer computational genius of machine learning, we're no longer just reacting to nature's chaos, we're actively anticipating it. And that leaves us with a truly fascinating question. If artificial intelligence can learn the complex, hidden language of a collapsing mountain, what other natural disasters can we outsmart next? I mean, the future of human and AI collaboration in disaster prevention is just getting started. Thank you so much for joining me for this explainer. Keep asking questions, and I'll catch you on the next deep dive.